Hi, I'm Simson Garfinkel. I'm the Senior Computer Scientist for Confidentiality and Data Access at the U.S. Census Bureau. I'm going to be talking to you today about our experiences implementing differential privacy for the 2020 census. This is the abstract of the talk that is here so that Google will find the slides and index them. And these are the acknowledgments. This is to remind you that this talk is the product of the work of many people working at the U.S. Census Bureau. So it's important to remember that differential privacy was invented in 2006, and that was 14 years ago. Now, 14 years seems like a long time, but it's not a long time since a fundamental scientific invention. And for comparison, I want you to think about the invention of public key cryptography, which was invented between 1976 and 1978. We are 14 years into differential privacy, but 14 years after the invention of public key cryptography was 2 years before Netscape Navigator came out with SSL. It was 3 years before SSH was invented and 4 years before PGP 3.0 came out. And going into the future, it wasn't until 2011 that the EFF pushed its HTTPS Now campaign and putting HTTPS everywhere. And that was 34 years after the invention of public key cryptography. So that's still 20 years in our future as far as differential privacy goes. Now, with that said, the Census Bureau deployed the first implementation of differential privacy in the world just 2 years after DP was invented. This is because we were able to adopt a system that we already had under development that used noise infusion to the new mathematics of differential privacy. But there were a lot more technical problems that we had to solve for the 2020 census than we had to solve for OnTheMap. Here's the most important slide. Despite all the work we've done, we still haven't met our users' expectations. And that's because data scientists are being trained to work with raw data, and they would probably get better results if they learned how to work with the direct results of differential privacy. Data users expect consistent data releases. We can make our data consistent, but that introduces much more error and degrades accuracy than if we were to release just the raw differential privacy measurements. Some users are calling the data that we release fake data, like fake news. That's not an accurate characterization of what we're doing. We're releasing synthetic data that is based on real data and which has had privacy protection mechanisms added. And our final problem has been it's really not clear how to do quality assurance and data exploration in a differential privacy framework. And so we're really looking to engage with the community on that issue, and that's really important for differential privacy moving forward. So because we all just went through this, we're familiar with the Decennial Census. It's the longest running statistical program in the world. It's the largest peacetime mobilization of labor in the United States. We just completed it last year, and the data will be released this year. And those data will be used to apportion the House of Representatives and to distribute somewhere between $675 billion and $1.5 trillion a year, according to various estimates. Now, our problem is that our challenge is that the Constitution requires that we collect this data, and Title 13, Section 9 of the U.S. Code requires that we maintain data confidentiality for the respondents whose information we collect. So to understand that requirement in terms of a statistical agency, imagine if there was a block that had 10 people living on it and they were all the same sex and all the same age. We could not publish an exact statistic that there were 10 people on the block with offering some sort of demonstration that the statistic protected confidentiality. If we didn't have that protection there and you knew that Allison lived on that block, then you'd immediately know that Allison was a woman and that Allison is 24. So at the Census Bureau, we use the term disclosure avoidance to describe this process of protecting confidential data. And we use that because the process is designed to prevent an improper disclosure under Title 13, Section 9. So previously, we used a technique called swapping to protect the information that we collected when we published it. And the problem with swapping was we couldn't release the actual details of the mechanism, and we couldn't release the parameters to tell people how much privacy protection it provided. With differential privacy, we can control that trade-off between privacy on the one side and very accurate data that we release on the other side. And with that change, we can now involve policymakers in the decision as to how much we should protect people's data versus how accurate should the data products be. And differential privacy is also future-proof. Our previous mechanism assumed that attackers that might want to re-identify people in the data had access to certain data sets and certain amounts of computer power. Differential privacy doesn't make any of those assumptions, and its guarantees don't depend upon limitations of the attackers. But each of these limitations ended up causing us problems. Many people within the Census Bureau thought that secrecy should remain an important part of our privacy protection mechanism. So when we moved to differential privacy, there were many concerns about actually publishing the source code. Likewise, differential privacy lets us control the privacy loss accuracy trade-off, but that meant we needed to develop tools to help policymakers make that decision, and we also needed to provide the policymakers with context and training to understand the decision that they were making. We needed to design our algorithms so that the accuracy would be where it was needed and not anywhere else, so that the privacy loss using differential privacy could be minimized. And then there's this issue of future-proof. We say that differential privacy is future-proof because the privacy definition guarantees that it makes a relative, not absolute. And this change in the sense of what it means to offer privacy also requires significant explanations and additional training. So the need to develop and tune the differential privacy algorithm was unlike anything that decennial response processing had ever done before. And that was before the pandemic. By 2017, we thought we had a good understanding of how differential privacy would fit into the census data processing pipeline. The plan was to simply replace the old privacy mechanism with the new one. For the 2010 census, we took the census edited file, applied our swapping mechanism, produced a set of microdata called the 100% file, and it was the confidential HDF that was tabulated for census publications. For the 2020 census, our plan was to use differential privacy to produce a newly named privacy-protected microdata detail file. One of our first big surprises was that different groups at the Census Bureau had different assumptions about what that would mean. Previously, every state was processed on a continuous flow basis, with the big states moving through and the small states moving through, all in their own way. But when we moved to differential privacy, the top-down mechanism that we designed required that all the states be computed upon at once. And this created a bottleneck in the decennial response processing because of the mechanism that we chose for differential privacy. And another impact of our mechanism is that it required significantly more computing power than the traditional tabulations. And this is because our mechanism required 800,000 privacy optimizations to be performed. Another challenge that we faced was that our differential privacy system had to be developed with real Title 13 protected data. Most of the systems for the 2020 census were developed using simulated data. And simulated data, by that we mean not based on protected respondent data. So the problem is that little work in the academic literature had been done using differential privacy to protect complex confidential data, So we needed to develop new algorithms that would work with data as complex as the United States. And in the US, there are clusters by age and race, there are multiracial households, there are same-sex unions, there's small group quarters and large group quarters, and they're all geographically diverse. So we needed to do this with real data, and that created privacy and confidentiality issues because we needed to do it on computers that were approved to hold that real data. This graph illustrates another problem that we encountered. If you're familiar with differential privacy, you know that this is a graph that shows how accuracy and privacy loss coexist with different values of epsilon. But to produce this graph, we need 5 to 10 runs of our system at each of those data points. So this graph is about 100 runs of the algorithm, and each of those runs requires 800,000 solves, as I previously mentioned. So this is a huge amount of computer time required to produce this relatively simple graph. So how did we do it? Well, the most important thing is that the Census Bureau leadership was 100% behind the move to differential privacy. John Thompson, director from 2013 to 2017, was instrumental in the move. He brought on board John Abowd as chief scientist for the purpose of implementing differential privacy, and John Abowd had tremendous support from Ron Jarman, who was performing the non-exclusive functions and duties of the director from 2017 to 2019, and who is now the Deputy Director and Chief Operating Officer. The initial implementation was done by Penn State professor Daniel Kiefer, who took a sabbatical at the US Census Bureau and built the first implementation of our top-down algorithm. In 2017, I joined the Census Bureau, and I engineered a framework from Dan's original ideas. And that framework is actually a system for building disclosure avoidance systems. It's a system for performing science experiments with plugins for the reader and the engine and the validator. And it's driven by a configuration file that allows us to easily experiment with parameters and plug in and plug out new code. And then in the 2018 end-to-end test, we put the source code release as specifications as an official data product. And this meant that the fact that we were releasing that data went through the process of approvals. The source code that we developed also could run from the 1940 census. That data has been publicly released. So we provided the general public with a way that they could run our software, even though they didn't have access to our confidential data. So initially, we were not approved for using Title 13 data for software development in the Amazon Web Services environment. That took work internally, and until we got there, we had to do our development with an on-premise Linux cluster. Eventually, we were able to move to Amazon Web Services, but we discovered that the software for monitoring execution of elastic MapReduce jobs in Amazon didn't provide the sufficient fidelity that we needed to develop and tune the algorithm. So we ended up creating our own dashboard, and each dashboard tracks all the running clusters that we have and each execution of the top-down algorithm. And during development, we have executed the algorithm tens of thousands of times. Each of the rectangles in the graph at the right represents an elastic MapReduce cluster. And as new clusters are created, they appear on this graph, and as they are deleted, they go away. So this graph shows the CPU utilization of the nodes in one of our EMR clusters. Each line represents the average CPU load of one of the nodes. There are 21 nodes, and each one has 96 cores. When the lines are over 96, those machines are overutilized, and when they're under 100, those machines are largely idle. And so you can see that for that section in the middle and the section on the right, we're well utilizing our cluster, but on the leftmost side and the rightmost side, the cluster is not being well utilized. And graphs like this allow us to tune the algorithm to get better machine utilization and lower clock times for the algorithm's execution. To help our data users understand the impact of differential privacy, we took the data from the 2010 census, processed it with a top-down algorithm, and published it. We then had a special workshop at the National Academies of Science in December 2019 to discuss the accuracy and the errors that were in the data that was part of that release. Now, a lot of the data users voiced concerns, and that was the subject of some articles in the popular media. In general, the 2010 demonstration data products were not well received. Our data users thought that differential privacy was introducing too much error into the data products. So the root of our problem is that we're adding random values which might be positive or they might be negative. So if we take a child's age and we add a random value, we might end up with a negative age. If we take an adult's age and we add a random value, we probably won't end up with a negative number. And this means that if you take ages and make sure that they're all going to be positive, you're introducing systematic bias. There's no way around that. The real solution here is to let the data users work with the noisy measurements. These are the clean data from the Ceph that have then had privacy-protecting noise added, but haven't yet gone through the consistency and interiorization process. We are now working with data users to give them access to these noisy measurement files in addition to the processed microdata. So in summary, differential privacy is now 14 years old, and even though the Census Bureau deployed the first differential privacy system just 2 years later, that was a new system that was designed from the beginning to use noise infusion, so it wasn't that heavy of a lift. For the 2020 census, we've had to retrofit the longest running statistical program in the world. And to do that has required support from the very top levels of the Census Bureau. It's required senior leadership and a significant scientific effort on the part of the entire Research and Methodology Directorate with the cooperation of the rest of the entire 2020 census team. It's been a lot of work, and we've worked eagerly and actively to involve data users as well. Data users have had some concerns, but we think that we will address them, and we think that people will be very pleased with the final product. So this was necessarily a very short talk, but you can get access to our current source code on GitHub, and you can also download our system specification and our scientific papers. And there's been a lot of public engagement, so here are some other talks that you might want to look at. So I really want to thank USENIX Enigma for allowing me to speak, and I'm ready to take questions.